So in this part, I would like to show you an additional example of calculating scattering parameters of an interesting network. This particular network is called a matched 3 dB attenuator. So let me actually explain each word slightly more. Let me start from the last one. An attenuator is a device whose main purpose is basically to attenuate power. And so that means that if I shoot this network with some power from port number 1, the power that should come out from port number 2 should be attenuated. By how much it should be attenuated is given by this number. So this is a 3 dB attenuator. That means that P2, the power that will come out from port 2, should be equal to half of my incident power in port number 1. 3 dB attenuators are not the only ones out there. There are 10 dB attenuators, 20 dB attenuators, if you want to basically attenuate the power by a factor of 10 or by a factor of 100, and of course more than that as well. Now finally we have this word here called matched, and essentially what that means is that as you're shooting power into port number 1 and you have terminated port number 2 in its own characteristic impedance, you should be getting basically zero power reflected. That's what a matched device actually is. So in the part of the course where I showed you, for example, the three-way splitter, the electrically small three-way splitter, this was not a matched device in the sense that there was reflection in ports 1, 2, and 3. The S11 was negative 1/3, which means that roughly about 11% of the incident power into port number 1 was coming back into port number 1, and that was not a matched device. As we're going to see here, by correctly selecting the resistance values R1, R2, and R3, then you can actually get a matched attenuator. The values have actually already been selected for you. There is a way we can actually solve these equations that you will see in a minute and get these numbers, but I just decided to give you the numbers and simply focus on calculating the S parameters for this network. So let's go through our calculation as we have basically seen before. I'm going to assume that by port number 2 is terminated to its own characteristic impedance, Z0, and then I'm going to calculate S11. Now you might say, 1 second, what exactly is Z0 here? I don't really see any ports, I don't really see any impedance. What is Z0? So as we have discussed before, when you have a lumped element like this, really the impedance Z0 is arbitrary. And so my advice in case of this question is to assume that Z0 is going to be equal to 50 ohms and express your S parameters in a 50 ohm system impedance. Now the good thing is that, as we will see later on, once you do know the S parameters for one reference impedance, let's say in this case 50 ohms, it's very simple to basically rescale them to a different reference impedance. And so you shouldn't be afraid to actually choose the impedance, even if later on the same network is actually utilized in a different system impedance. You can simply rescale the S parameters. So here I'm going to calculate them based on a 50 ohm impedance, and as we have seen before, once I terminate my port 2 to Z0 of 50 ohms, then all I have to do is calculate my S11 as the reflection coefficient in port number 1. So in other words, S11 will be B1 divided by A1, and that means it's going to be equal to Z in minus Z0 over Z in plus Z0. So the problem now basically boils down to finding what is the input impedance that you see into port number 1, and that is easily done. It's basically sophomore level combining impedances, and if you basically do the calculations and you assume that Z0 is equal to 50 ohms, this will end up being equal to 50 ohms. So there you have it. We basically found out that if my Z0 is 50 ohms, and if I choose my impedances, my resistances rather, the values that you see in this figure, my S11 will actually be equal to 0. So that essentially justifies the word matched that I used right here, is that the attenuator is matched from port number 1, and of course it will be matched in port number 2. This is a totally symmetric network, so this is going to be equal to S22 as well. Now my next step, once I found out my S11 and S22, is find the S21 and S12. This is a reciprocal network in addition to being symmetric, which basically means that my S12 will be equal to S21, so I will only focus on finding the S21. So as I did for the electrically small T junction, I will essentially do the process very formally so you get acquainted with this and you can apply it yourself. So I will again terminate my impedance number 2 to 50 ohms, my Z naught. I will write down the voltage in port number 2. This is the voltage V2. I will write down the voltage in port number 1. This is V1. And I will have to find the relationship between these two voltages. This will be the key to essentially unlocking the S21 calculation. Finding the V1 and V2 is actually very simple because, again, it's a voltage division. So I know that you all know how to do that. So now let's go ahead and formally apply the equations. So V2 is going to be equal to Z naught A2 plus B2. A2 is equal to 0 because of the termination. That means that V2 is going to be equal to square root of Z naught, 50 ohms in this case, times B2. Similarly, V1 is going to be equal to Z naught A1 plus B1, and I have calculated right now the S11 from above, and so that means that this will be equal to Z naught 1 plus S11 A1. That is exactly what I had done for the electrically small T-junction, the electrically small three-way splitter. Nothing has changed so far. Again, what will change is that once I divide those two equations to get essentially the ratio of B2 by A1, which is what I really care about for S21, I will need to know the relationship between V2 and V1, where again the voltages are given in the figure here. And from a voltage division perspective, V2 is going to be nothing less than 0.707 V1. So if I basically do this calculation, S2 is going to be equal to B2 by A1, and this number here is going to be equal to 0.707. And as I mentioned before, this will be equal to S12 due to reciprocity. So I'm basically done. I have essentially found out that my S21 is equal to 0.707. And as you can imagine, that basically means that I have my 3 dB attenuator because the S21 square is basically 1/2. So indeed, if I look into my incident power into port number 1, as I basically did from a definition point of view, the P incident will be equal to A1 square divided by Z naught. And if I look at the output power in port number 2, P output will be equal to P2 square divided by Z naught. Here's the A1 and the B2. The B2 is equal to S21 square times A1 square. That is true, of course, provided that my port number 2 is terminated to its own characteristic impedance, so provided my A2 is equal to 0, which now that I know my S21 to be equal to 0.707, the result will be equal to incident power divided by 2. Now this completes the calculation for the 3 dB attenuator, but you may be thinking the question, well, if I am going to utilize the 3 dB attenuator, why? Why on earth do I really need that? Why do we need attenuators, in other words? So there are actually different reasons for using attenuators. In the beginning, it might appear as a little bit odd, since in real life, it's kind of hard to generate RF power, so it might appear silly to actually waste it in an attenuator. But you need to remember that there are cases where this is necessary. For example, in measurements and instrumentation, 3 dB attenuators are quite useful because at some point you may realize that the power you're actually shooting to your device is too high. You may burn it. You may damage it. In that case, you do need to attenuate it, and we do choose attenuators to do that. In fact, in instrumentation, it's very common to have what we call variable attenuators. So there's a little knob that you can actually tweak to change the attenuation level. For the same reason, we actually want matched attenuators, because once you basically shoot power to an attenuator, if this power might be too high to damage your device under test, you definitely don't want any of this high power to come back to you. And so having a matched 3 dB attenuator, or matched any type of an attenuator, is actually quite necessary to avoid any accidental damage. So you might say, well, okay, I understand why we use attenuators. Power might be a little bit too high sometimes. Where does this power go? You just told me that the output power is only 50% of the instant power. What is the other 50%? Well, the other 50% is actually consumed in these impedances. So you don't see it as a reflected power, but you will see it as a consumed power in your attenuator, which basically means that your attenuator will heat up. So when you make balanced attenuators, it's very, very critical to protect them from a heat transfer point of view, from a heat dissipation point of view. So we do design networks, if the power is truly high, to make sure that they can dissipate the power they consume, and so there is no damage there.